Hi, this is the lecture on periodic table. We've spent a lot of time on this chapter. It is going to be in two basic parts. The first part is going to be simply information on the periodic table. And then the second part will be very conceptual. Ionization energy, atomic and ionic radii, and electronegativity. All right, let's begin right away. In 1916, a self-service grocery store opened in Memphis, Tennessee. Shoppers could select items from shelves instead of waiting for a clerk to gather the items for them. In a self-service store, the customers must know how to find the products. From your experience, you know that products are grouped according to similar characteristics. You don't expect to find fresh fruit with canned fruit or bottled juice with frozen juice. With a logical classification system, finding and comparing products is easy. In this section, you will learn how elements are arranged in the periodic table and what that arrangement reveals about the elements. That's the whole point of the periodic table. With an arrangement of the elements, you can figure out so much more about chemistry than if you had this random, chaotic information all over the place. So the organization of the periodic table by the early scientists will provide a useful tool to expand our knowledge of chemistry and our understanding of the connections among the elements. A few elements have been known for thousands of years, including copper, silver, and gold. Yet only 13 elements had been identified by the year 1700. Chemists suspected that other elements existed. They had even assigned names to some of those elements, but they were unable to isolate the elements from their compounds. As chemists began to use scientific methods to search for elements, the rate of discovery increased. In one decade, from 1765 to 1775, chemists identified 5 new elements, including 3 colorless gases: hydrogen, nitrogen, and oxygen. That's the mid-1800s. Searching for an organizing principle. Was there a limit to the number of elements? How would chemists know when they had discovered all the elements? To begin to answer these questions, chemists needed to find a logical way to organize the elements. Chemists used the properties of elements to sort them into groups. In 1829, a German chemist, J. W. Dobereiner, published a classification system. In his system, elements were grouped into triads. A triad is a set of 3 elements with similar properties. So this begins the search for the periodic table. The elements in figure 1, that's on the next page, formed one triad: chlorine, bromine, and iodine. May look different, but they have very similar chemical properties. For example, they react easily with metals. Dobereiner noted a pattern in his triads. One element in each triad tended to have properties with values that fell midway between those of the other 2 elements. For example, if you add them and divide by 2, that's 81.177. This value is close to the atomic mass of bromine, which is 79.9 AMU. Unfortunately, all the known elements could not be grouped into triads. Chlorine, bromine, and iodine have very similar chemical properties. The numbers shown with the average atomic masses for these elements. We usually use 35 for chlorine, mass number, just makes calculations easier. Bromine is 80 we usually use, and iodine 127. Unless you're doing quantitative work, very high analytical quantitative work, just use those. From 1829 to 1869, different systems were proposed, but none of them gained wide acceptance. In 1869, a Russian chemist and teacher, Dmitry Mendeleev, published a table of the elements. Later that year, a German chemist, Lothar Meyer, published a nearly identical table. Mendeleev was given more credit than Meyer because he published his table first, and because he was better able to explain its usefulness. The stamp in Figure 2 on the next page is one of many ways that Mendeleev's work has been honored. Mendeleev developed his table while working on a textbook for his students. Here's the stamp. Dmitry Mendeleev proposed a periodic table that could be used to predict the properties of undiscovered elements. So Mendeleev could be considered the father of the periodic table. The grandfather, let's say, of the periodic table, because we have other scientists who helped to develop the periodic table as we know now, that know more than Mendeleev did. But Mendeleev knew what he knew and did well with what he had known. He needed a way to show the relationships among more than 60 elements. He wrote the properties of each element on a separate note card. This approach allowed him to move the cards around until he found an organization that would work. The organization he chose was a periodic table. Elements in a periodic table are arranged into groups based on a set of repeating properties. Mendeleev arranged the elements in his periodic table in order of increasing atomic mass. Figure 3 on the next page is an early version of Mendeleev's periodic table. Look at the column that starts with Ti 50. In this early version of Mendeleev's periodic table, the rows contain elements with similar properties. Observing a fourth element is grouped with chlorine, bromine, and iodine. What is this element's symbol? Okay, let's look at Ti 50, and let's look at a fourth element is grouped with chlorine, bromine, and iodine. Okay, so let's see. Let's look at Ti 50. Here's Ti 50: titanium, vanadium, going down to chromium, magnesium, and then you have chlorine, bromine, and iodine. Okay, so you have chlorine, you have some question marks there under zinc, 68, 70. Then there's bromine, 80. So notice the two question marks between the entries for zinc and arsenic. Mendeleev left these spaces in his table because he knew that bromine belonged with chlorine and iodine. He predicted that elements would be discovered to fill those spaces, and he predicted that their properties would be based on their locations in the table. So let's go back and take another look at these elements just for a moment. So here we have the table again, and instead of columns, it's rows. Rows are columns and columns are rows. So let's look at chlorine, bromine, and iodine, and to the left is fluorine. That's grouped with it. Look at lithium, sodium, potassium, rubidium, cesium. It's pretty amazing what he did. They're all very similar. Manganese, etc. It's unbelievable. The elements between zinc and arsenic were gallium and germanium, which were discovered in 1875 and 1886, respectively. There was a close match between the predicted properties and the actual properties of these elements. This match helped convince scientists that Mendeleev's periodic table was a useful tool. And so the hunt for more elements began, and the current table began to take shape. The atomic mass of iodine is 126.90. The atomic mass of tellurium is 127.60. Based on its chemical properties, iodine belongs in a group with bromine and chlorine. So Mendeleev broke his rule and placed tellurium before iodine in his periodic table. He assumed that the atomic mass for iodine and tellurium were incorrect. but they were not. Iodine has a smaller atomic mass than tellurium does. A similar problem occurred with other pairs of elements. It's amazing that his placement actually worked relative to our understanding of protons. The problem wasn't with the atomic masses, but with using atomic mass to organize the periodic table. Mendeleev developed his table before scientists knew about the structure of atoms. He didn't know that the atoms of each element contain unique numbers of protons. Remember that the number of protons is the atomic number. In 1913, a British physicist, Henry Moseley, determined an atomic number for each known element. Tellurium's atomic number is 52, and iodine's is 53. So it makes sense for iodine to come after tellurium in the periodic table. So the difference in the two tables is based on protons. In the modern periodic table, elements are arranged in order of increasing atomic number. The elements in Figure 4, next page, are arranged in order of atomic number, starting with hydrogen, which has an atomic number of 1. There are 7 rows or periods in the table. Period 1 has 2 elements. Period 2 has 8 elements. Period 4 has 18 elements. And period 6 has 32 elements. Each period corresponds to a principal energy level. There are more elements in higher numbered periods because there are more orbitals in higher energy levels. So now let's look at the periodic table that started to take shape. See that it's a bit clumsy looking relative to what we know today. In the modern periodic table, the elements are arranged in order of increasing atomic number. Interpreting diagrams. How many elements are there in the second period? There are 8. There are 8. Lithium, beryllium, etc. That particular period. Okay. Let's begin again. Recall the rules you studied in Chapter 5 for how electrons fill orbitals. The elements within a column or group in the periodic table have similar properties. The properties of the elements within a period change as you move across a period from left to right. However, the pattern of properties within a period repeats as you move from one period to the next. This pattern gives rise to the periodic law. When elements are arranged in order of increasing atomic number, there is a periodic repetition of their physical and chemical properties. When elements are arranged in order of increasing atomic number, there is a periodic repetition of their physical and chemical properties. Most periodic tables are laid out like the one in Figure 5 on the next page. Some elements from period 6 and 7 are placed beneath the table. This arrangement makes the periodic table more compact. It also reflects an underlying structure of the periodic table, which you will study in section 6.2. Each group in the table in Figure 5 has 3 labels. Scientists in the United States use the label shown in red. Scientists in Europe use the labels shown in blue. There is some overlap between the systems, but in many cases, 2 different groups have the same letter and number combination. Figure 5, one way to classify elements in the periodic table is as metals, nonmetals, and metalloids, inferring what is the purpose for the black stair-step line. Well, those are the metalloids. That is the separation between metals and nonmetals. Now, what we're going to look at is the modern periodic table that Glenn Seaborg helped to develop, for which he won the Nobel Prize. So here we have the modern periodic table, metals on the left, nonmetals on the right, metalloids down the stair step, boron, silicon, germanium, arsenic, antimony, tellurium, astatine. Okay, so those, and then underneath are the rare earth metals, made the reading of the periodic table a little easier, makes it more compact to take them out of the body of the table. For scientists to communicate clearly, they need to agree on standards they will use. The International Union of Pure and Applied Chemistry, IUPAC, is an organization that sets standards for chemistry. In 1985, IUPAC proposed a new system for labeling groups in the periodic table. They numbered the groups from left to right, 1 through 18, the black labels in Figure 5. The large periodic table in Figure 9 includes the IUPAC system and the system used in the United States. The latter system will be most useful when you study how compounds form in Chapter 7 and Chapter 8. We will use 1 through 18. Dividing the elements into groups is not the only way to classify them based on their properties. The elements can be grouped into 3 broad classes based on their general properties. 3 classes of elements are metals, nonmetals, and metalloids. Across a period, the properties of the elements become less metallic and more nonmetallic. Metals, the number of yellow squares in Figure 4, shows that most elements are metals, about 80%. Metals are good conductors of heat and electric current. A freshly cleaned or cut surface of a metal will have a high luster or sheen. The sheen is caused by the metal's ability to reflect light. All metals are solid at room temperature except for mercury. Many metals are ductile, meaning they can be drawn into wires. Most metals are malleable, meaning they can be hammered into thin sheets without breaking. Figure 6 on the next page shows how the properties of metals can determine how metals are used. Figure 6. The metals iron, copper, and aluminum have many important uses. How each metal is used is determined by its properties. Aluminum, Al. Aluminum is one of the metals that can be shaped into a thin sheet or foil. To qualify as a foil, a metal must be no thicker than approximately 0.15 millimeters. Copper, Cu. Copper is ductile and second only to silver as a conductor of electric current. The copper used in electric cables must be 99.99% pure. Iron. The Gateway Arch in St. Louis, Missouri is covered in stainless steel containing iron and 2 other metals, chromium and nickel. The steel is shiny, malleable, and strong. It also resists rusting because it's stainless steel. There's the Gateway Arch in St. Louis. There's some copper in the upper right, and there is some aluminum cooking what looks to be a turkey. And you'll notice one of the properties of aluminum specifically, especially aluminum foil, even if it's in the oven for hours, if you go and reach for that foil, it really doesn't burn you. Pretty amazing stuff. There's a better picture. Looks like a turkey, Thanksgiving turkey, being cooked for dinner. And it's in a little bit of a tent. What does that do? How does that help to cook the bird? Interesting lesson on thermodynamics that we'll talk about at a later date. But one of the most amazing things about it is that it really, really, really does not get very hot. Nonmetals. Figure 5, blue, is used to identify the nonmetals. These elements are in the upper right corner of the periodic table. There is a greater variation in physical properties among nonmetals than among metals. Most nonmetals are gases at room temperature, including the main components of air, nitrogen, and oxygen. A few other solids, such as sulfur and phosphorus. One nonmetal, bromine, is a dark red liquid. The variation among nonmetals makes it difficult to describe one set of general properties that will apply to all nonmetals. However, Nonmetals are not metals, as their name implies. So they tend to have properties that are opposite to those of metals. In general, nonmetals are poor conductors of heat and electric current. Carbon is an exception to this rule. Solid nonmetals tend to be brittle, meaning they will shatter if hit with a hammer. Metalloids. There is a heavy stair-step line in Figure 5 that separates the metals from the nonmetals. Most of the elements that border this line are shaded green. These elements are metalloids. A metalloid generally has properties that are similar to those of metals and nonmetals. Metals and nonmetals, those are metalloids. Under some conditions, a metalloid may behave like a metal. Under other conditions, it may behave like a nonmetal. The behavior often can be controlled by changing the conditions. For example, pure silicon is a poor conductor of electric current, like most nonmetals. But if a small amount of boron is mixed with silicon, the mixture is a good conductor of electric current, like most metals. Silicon can be cut into wafers, like those being inspected in Figure 7 on the next page, and used to make computer chips. Silicon is the basis for the computer chip. When they say chip, it's like a chip, literally like a chip, and it's made of silicon. Here's a picture of a silicon chip. 6-inch, very big, 6-inch wafer of silicon wafers are the Gothic cathedrals of our age. They are the most sophisticated, most beautiful, and most important physical object created by humankind around the turn of the millennium. They are created in huge numbers in sizes from 2-inch to 12-inch, and most are cut up into individual chips. A few defective ones are taken out of the line before that stage and sold in museum shops and on eBay, where I got this one and quite a few others, purity greater than 99.99999. Figure 7, pancake-sized circular slices of silicon called wafers are used to make computer chips. Because a tiny speck of dust can ruin a wafer, the people who handle the wafers must wear bunny suits. The suits prevent skin, hair, or lint from clothing from entering the room's atmosphere. Here is the bunny suit on the right. I'm not quite sure how much of a bunny suit it is. Looks more like level 4 contagion suite in the Center for Disease Control in Atlanta. But then there is the microchip that they are protecting, the silicon wafer, keeping it clean. So they go to a lot of expense to make these computer chips. The sculptor Augustus Saint Gaudens designed this gold coin at the request of Theodore Roosevelt. President Roosevelt wanted coins minted in the United States to be as beautiful as ancient Greek coins, which he admired. The coin is an example of a double eagle. The name derives from the fact that the coin was worth twice as much as the $10 coins called eagles. A coin may contain a lot of information in a small space. Its value, the year it was minted, and its country of origin. Each square in a periodic table also contains a lot of information. In this section, you will learn what types of information are usually listed in a periodic table. So the periodic table is a clearinghouse for chemistry information. And here is a picture of those coins commissioned by President Roosevelt and designed by Mr. Augustus Saint Gaudens. The periodic table displays the symbols and names of elements along with information about the structure of their atoms. Figure 8 in the next slide shows one square from the detailed periodic table of the element in Figure 9. In the center of the square is the symbol for sodium. The atomic number for sodium, 11, is above the symbol. The element name and average atomic mass are below the symbol. There is also a vertical column with the numbers 2, 8, and 1, which are the number of electrons in each occupied energy level of the sodium atom. Figure 8, this is the element square for sodium from the periodic table in Figure 9. Interpreting diagrams. What does the data in the square tell you about the structure of the sodium atom? I had to kind of read this twice. In other words, the Figure 8 is an example from Figure 9. Figure 9 is the big kahuna, the big periodic table. So the next slide will be Figure 8, which is an example from Figure 9 and the complete periodic table. Here is Figure 8. Sodium, 11 is the atomic number. It has 3 shells. The last one is 3s1, that's where the 1 comes from. So it'd be 1s2, 2s2, 2p6, that's the 8 in the second shell, and then 3s1. The symbol is Na, and its mass is 22.990. That's the average atomic mass. The symbol for sodium is printed in black because sodium is a solid at room temperature. In Figure 9, next page, the symbols for gases are in red. The symbols for the two elements that are liquids at room temperature, mercury and bromine, are in blue. The symbols for some elements in Figure 9 are printed in green. These elements are not found in nature. In Chapter 25, you will learn how scientists produce these elements. The background colors in the squares are used to distinguish groups of elements. For example, 2 shades of gold are used for the metals in groups 1A and 2A. Figure 9, in this periodic table, the colors of the boxes are used to classify representative elements and transition elements. So not only does the placement of the periodic table, the placement of the elements in the periodic table relative to each other element tell you a lot, but you can also use shading to help further define properties in the periodic table. You see how those light green elements, the heavier ones, those are synthetic. Those are made in a laboratory. So you can see the different colors that can make a periodic table even more useful. You have the placement of sodium relative to magnesium, beryllium, lithium, potassium, and calcium. You have it in 1A or 1, and that tells you a lot as well as the color of that column. The group 1A elements are called alkali metals, and the group 2A elements are called alkali earth metals. The name alkali comes from the Arabic al-akali, means the ashes. Wood ashes are rich in compounds of the alkali metals sodium and potassium. Some groups of nonmetals also have special names. The nonmetals of group 7A, for instance. The name halogens comes from the combination of the Greek words hal, meaning salt, and the Latin word genesis, meaning to be born. There is a general class of compounds called salts, which include the compounds called table salt, chlorine, bromine, and iodine. The most common halogens can be prepared from their salts. Electrons play a key role in determining the properties of elements, so there should be a connection between the element's electron configuration and its location in the periodic table. Elements can be sorted into noble gases, representative elements, transition metals, or intertransition metals based on their electron configurations. You may want to refer to Figure 9 as you read about these classes of elements. The noble gases, the blimp in Figure 10 on the next page is filled with helium. Helium is an example of a noble gas. The noble gases are the elements in group 8A or 18 of the periodic table. This blimp contains helium, one of the noble gases. Applying concepts. What does the ability of a helium-filled blimp to rise in air tell you about the density of helium? Helium is not very dense. It's too bad that at one time the United States had the monopoly on helium, and many countries had to fly their dirigibles with hydrogen, leading to catastrophic failure, explosions. Is terrible. Helium is a little bit more dense, not much more dense than hydrogen. But hydrogen, as you will learn if you don't know already, is extremely flammable. Extremely flammable. There was the Hindenburg disaster in New Jersey in the 1930s was an example of this catastrophic failure of hydrogen. These nonmetals are sometimes called the inert gases because they rarely take part in a reaction. The electron configurations for the first four noble gases in group 8A are listed below. Look at the description of the highest occupied energy level for each element, which is highlighted in yellow. The S and P sublevels are completely filled with electrons. Chapter 7 will explain how this arrangement of electrons is related to the relative inactivity of the noble gases. The representative elements, figure 11 on the next page, shows the portion of the periodic table containing groups 1A through 7A. 1A through 7A. Figure 11, some of the representative elements exist in nature as elements. Others are found only in compounds. Magnesium, the magnified view of a leaf shows the green structure where light energy is changed into chemical energy. The compound chlorophyll, which contains magnesium, absorbs the light. Arsenic, the bright red ore, is a major source of arsenic in the Earth's crust. It contains a compound of arsenic and sulfur. When salt lakes evaporate, they form salt pans, like this one in Death Valley, California. The main salt in a salt pan is sodium chloride, sulfur. These scientists are sampling gases being released from a volcano through a vent called a fumarole. The yellow substance is sulfur. The yellow substance is sulfur. Elements in these groups are often referred to as representative elements because they display a wide range of physical and chemical properties. Some are metals, some are nonmetals, and some are metalloids. Most of them are solids, but a few are gases at room temperature, and one, bromine, is a liquid. In atoms of representative elements, the S and P sublevels of the highest occupied energy level are not filled. Let me repeat that. In atoms of representative elements, the S and P sublevels of the highest occupied energy level are not filled. We're talking about the electron configurations in groups. Look at the electron configuration for lithium, sodium, potassium. In atoms of these groups 1A elements, there is only one electron in the highest occupied energy level. The electron is in an S sublevel. The atoms of carbon, silicon, and germanium in group 4A, there are 4 electrons in the highest occupied energy level. For any representative element, its group number equals the number of electrons in the highest occupied energy level. If you're going to use the American model, I actually prefer to use the European model, and just understand where the s and the p's are, and the number of valence electrons are the s and p's based on the position in the periodic table. In the periodic table, the B groups separate the A groups on the left side of the table from the A groups on the right side. Elements in B groups, which provide a connection between the two sets of representative elements, are referred to as transition elements. These are two types of transition elements: transition metals and inner transition metals. They are classified based on their electron configurations. The transition metals are the group B elements that are usually displayed in the main body of the periodic table. Again, it's 3 through 12. Copper, silver, gold, and iron are transition metals. In atoms of a transition metal, the highest occupied S sublevel and a nearby D sublevel contain electrons. These elements are characterized by the presence of electrons in D orbitals. The inner transition metals appear below the main body of the periodic table. In atoms of an inner transition element, the highest occupied S sublevel and a nearby F sublevel generally contain electrons. The inner transition metals are characterized by F orbitals that contain electrons. So the Fs are being filled in the inner transition metals. Before scientists knew much about inner transition metals, people began to refer to them as rare earth elements. This name is misleading because some inner transition metals are more abundant than other elements. Blocks of elements. If you consider both the electron configurations and the positions of the elements in the periodic table, another pattern emerges. In Figure 12, the next page, the periodic table is divided into sections or blocks that correspond to the highest occupied sublevels. The S block contains the elements in groups 1A and 2A and the noble gas helium. Figure 12. The diagram classifies elements into blocks according to the sublevels that are filled or filling with electrons, interpreting diagrams. In the highest occupied energy level of a halogen atom, how many electrons are in the P sublevel? We'll count it. It is going from left to right, it's the fifth column for the P. It's the fifth column for the P, as the next figure will show. So it's P5. So that's going to be the halogen. So the P's are being filled. This should be a review for what I like to call NLX, the final energy level, sub-energy level, and the number of electrons in the sub-energy level. So, for instance, if you look at scandium, upper left of the green section, it's going to be D1. It goes 3, 4, 5, 6, so it'll be 3D1. 3D1. The P block contains the elements in groups 3A, 4A, 5A, 6A, 7A, and 8A, with the exception of helium. The transition metals belong to the D block, and the inner transition metals belong to the F block. You can use Figure 12 to help determine electron configurations of elements. Each period on the periodic table corresponds to a principal energy level. Say an element is located in period 3. You know that the S and P sublevels in energy levels 1 and 2 are filled with electrons. You read across period 3 from left to right to complete the configuration, as we did in Chapter 5. Transition elements. For transition elements, electrons are added to a D sublevel with a principal energy level that is 1 less than the period number. For the inner transition metals, the principal energy level of the F sublevel is 2 less than the period number. This procedure gives the correct electron configuration for most atoms. True colors. Here is an example of how elements are used in nature relative to coloring. Paint consists essentially of a pigment, a binder, and a liquid in which the other components are dissolved or dispersed. The liquid keeps the mixture thin enough to flow. The binder attaches the paint to the surface being painted, and the pigment determines the color. Pigments may be natural or manufactured. They may be inorganic or organic. The same pigment can be used in a water-based or oil-based paint. Comparing and contrasting. Describe at least three differences between the cave paintings and the paintings by Jacob Lawrence. Natural pigments. A prehistoric artist had a limited choice of colors: black from charcoal and red, brown, and yellow from oxides of iron in the Earth's crust. These oxides, or ochre, pigments are often referred to as earth tones. Here's charred wood is a source of charcoal. Here's an example of yellow ochre and red ochre. You can see how an answer to the comparing and contrasting question has already been done, at least the differences. Here are the cave paintings. You can see the earth tones and the black that are very dominant in this example of some kind of buffalo or oxen or something that was painted on the cave. This example, this prehistoric art around 1400 years ago, an artist painted this bison on the ceiling of a cave in Spain. It is about 2 meters long. And here on the next slide, we have red iron oxide, cadmium orange, cobalt yellow, zinc white, chromium oxide green, cobalt blue, and manganese violet. Manufactured pigments, alchemists and other chemists made pigments that don't exist in nature. They also made purer versions of natural pigments. Many of these pigments contain transition metals such as the manganese, cobalt, chromium, zinc. There's another cobalt, cadmium, and iron. Those are all transition elements for the artist to use. From pigments to paint, artists mix manufactured pigments with binders and solvents to make paint. Although pre-mixed paints become available around 1800, some artists, including Jacob Lawrence, continued to mix their own paint. Here's an example of a painting, The Builders, 1974, by Jacob Lawrence. And the next slide, you'll see a little bit more clearly, you have red iron oxide, that's iron 3 oxide. We'll look at that in chapter 9 when we talk about nomenclature. Cadmium orange, solid solution of cadmium selenide, CdSe, and cadmium sulfate, CdSO4. Cobalt yellow, that is potassium cobalt nitrate. That's kind of a complex looking collection of atoms making a compound. You have zinc white, which is zinc oxide. You put that also on your nose in the summertime. If you have light skin, you have chromium oxide green, which is chromium 3 oxide. Cobalt blue, which is cobalt 2 aluminate. AlO2 is aluminate. That's called a polyatomic ion. Manganese violet, manganese ammonium pyrophosphate. Look at that mess. Mn, Roman numeral 3, and then ammonium pyrophosphate. Kind of complex looking. Amazing what the different elements can do in our lives. Amazing. An atom doesn't have a sharply defined boundary, so the radius of an atom cannot be measured directly. There are ways to estimate the sizes of atoms. In one method, a solid is bombarded with X-rays, and the paths of the X-rays are recorded on film. Sodium chloride, table salt, produced the geometric pattern in the photograph. Such a pattern can be used to calculate the position of nuclei in a solid. The distances between the nuclei in a solid are an indication of the size of the particles in the solid. In this section, you will learn how properties such as atomic size are related to the location of elements in the periodic table. And here is a shot of the crystallography test of sodium chloride. Now, another way to think about atomic size is to look at the units that form when patterns of the same element are joined to one another. These units are called molecules. Figure 13 on the next slide shows models of molecules, molecular models, for 7 nonmetals. Because the atoms in each molecule are identical, the distance between the nuclei of these atoms can be used to estimate the size of the atoms. This size is expressed as an atomic radius. The atomic radius is 1/2 of the distance between the nucleus of the two atoms of the same element when the atoms are joined, the atomic radius. Actually, half of the sphere, you would say. Figure 13, this diagram lists the atomic radii of 7 nonmetals. And an atomic radius is half the distance between the nuclei of the two atoms of the same element when the atoms are joined. So you can see P means pico or picometers. That's 10 to the negative 12th. 1 picometer is 10 to the negative 12th meters. Very small. The distances between atoms in a molecule are extremely small. So the atomic radius is often referred to as in picometers or picometers. Recall that there are 1 trillion or 10 to the 12th picometers in a meter. The molecular model of iodine in figure 13 is the largest. The distance between the nuclei in an iodine molecule is 280 picometers. Because the atomic radius is 1/2 the distance between the nuclei, a value of 140 is assigned as the radius of the iodine atom. In general, atomic size increases from top to bottom within a group or family and decreases from left to right along the period of the periodic table. Group trends in atomic size in the figure 14 on the next page graph. Atomic radius is plotted versus atomic number. Look at the data from the alkali metals and noble gases. The atomic radius within these groups increases as the atomic number increases. This increase is an example of a trend. As the atomic number increases within a group, the charge on the nucleus increases and the number of occupied energy levels increases. These variables affect atomic size in opposite ways. The increase in positive charge draws electrons closer to the nucleus. Positive charge draws electrons closer to the nucleus. Figure 14, the graph plots atomic radius versus atomic number for 55 elements, analyzing the data. Which alkali metal has an atomic radius of 238? Drawing conclusions based on the data for alkali metals and noble gases. How does atomic size change within a group? Predicting, is an atom of barium, atomic number 56, smaller or larger than an atom of cesium, capital C, small s. Here's the graph. You can see how, as you go down the column, the lithium, sodium, potassium, rubidium, cesium, they're the largest, and they become larger as you go down. But as you go within a period, lithium down to neon, sodium down to argon, you see that as you go from left to right across the period, the radius decreases. The radius decreases. The increase in the number of occupied orbitals shields electrons in the highest occupied energy level from the attraction of protons in the nucleus. The shielding effect is greater than the effect of the increase in nuclear charge, so the atomic size increases. Periodic trends in atomic size. Look again at figure 14. In general, atomic size decreases across a period from left to right. Each element has one more proton and one more electron than the preceding element. Across a period, the electrons are added to the same principal energy level. Very important. The shielding effect, it's called the shielding effect, should have a capital S and a capital E there, is constant for all the elements in a period. The increasing nuclear charge pulls the electrons in the highest occupied energy level closer to the nucleus, and the atomic size decreases. Figure 15, next page, summarizes the group and period trends in atomic sizes. So, we're getting near the end here. Figure 15. The size of atoms tends to decrease from left to right across a period and increase from top to bottom within a group, predicting if a halogen and an alkali metal are in the same period, which one will have the larger radius? Which one will have the larger radius? Here are trends in atomic size. Size generally decreases going from left to right in a period. Size generally increases going from top to bottom. You have the nonmetals are in black and the metals are in yellow, and that's pretty much it. You'll find that the ionic sizes vary differently. Some compounds are composed of particles called ions. An ion is an atom or group of atoms that has a positive or negative charge. An atom is electrically neutral because it has equal number of protons and electrons. For example, an atom of sodium has 11 positively charged protons and 11 negatively charged electrons. The net charge on a sodium atom is 0. Positive and negative ions form when electrons are transferred between atoms. Atoms of metals, such as sodium, tend to form ions by losing one or more electrons from their highest occupied energy level. Sodium will lose one because it's in group 1. A sodium atom tends to lose one electron. Figure 16, next page, compares the atomic structure of a sodium atom and a sodium ion. In the sodium ion, the number of electrons, 10, is no longer equal to the number of protons, 11, because there are more positively charged protons than negatively charged electrons. The sodium has a net positive charge. An ion with a positive charge is called a cation. The charge for a cation is written as a number followed by a plus sign. I use the plus sign first. That's just me. If the charge is 1, the number 1 is usually omitted from the symbol for the ion. Figure 16, when a sodium atom loses an electron, it becomes a positively charged ion. When a chlorine atom gains an electron, it becomes a negatively charged ion. Interpreting diagrams. What happens to the protons and neutrons during these changes? What happens to the protons and neutrons during these changes? Is there anything that happens? Here is an example of you lose an electron and you're going to be positive. That's a sodium. And here the chlorine atom is going to gain an electron, and you're going to get a negative 1 charge. Keep this in mind when we talk in Chapter 7 about ionic bonding. This will help explain that whole concept. You really have to know your ions. So, sodium plus 1 is equivalent to sodium plus 1. Atoms of nonmetals, such as chlorine, tend to form ions by gaining 1 or more electrons. A chlorine atom tends to gain 1 electron. Figure 16 compares the atomic structure of chlorine and a chloride ion. In a chloride ion, the number of electrons, 18, is no longer equal to the number of protons. Because there are more negatively charged electrons than positively charged protons, the chloride ion has a net negative charge. An ion with a negative charge is called an anion. The charge for an anion is written as a number followed by a minus sign, or I simply like to use an integer and say -1. Recall that electrons can move to higher energy levels when atoms absorb energy. Sometimes there is enough energy to overcome the attraction of the protons in the nucleus. The energy required to remove an electron from an atom is called ionization energy. This energy is measured when an element is in its gaseous state. The energy required to remove the first electron from an atom is called the first ionization energy. The cation produced has a +1 charge. First ionization energy tends to decrease from top to bottom, because the electrons are more loosely held in the larger atoms within a group, and increase from left to right across a period. The closer the structure becomes like a noble gas. Table 1 on the next page lists the first, second, and third ionization energies for the first 20 elements. The second ionization energy is the energy required to remove an electron from an ion with a +1 charge. The ion produced has a +2 charge. The third ionization is the energy required to remove an electron from an ion with a +2 charge. The ion produced has a +3 charge. The ionization energy can help you predict what ions elements will form. Look at the data in Table 1 for lithium, Li, sodium, Na, and potassium K. So here are the Table 1 shows the first, second, and third ionization energies for each of them. Look at the noble gases, how high they are, and how high the first, second, and third ionization energies are for those. And the graph of these will be very telling when you look at the peaks and valleys and the flatter regions of the graphs. The increase in energy between the first and second energies is large. It is relatively easy to remove 1 electron from a group 1A metal atom, but it is difficult to remove a second electron. So, group 1A metals tend to form ions with a +1 charge. Group trends in ionization energy, figure 17, is a graph of first ionization energy versus atomic number. Each red dot represents the data for 1 element. Look at the data for the noble gases and the alkali metals. In general, first ionization energies decreases from top to bottom within a group. Notice I'm saying where it says, so group 1A metals tend to form ions with that should be a +1 charge. Anytime you have an ionization energy taking away an electron, it's a +1 charge. That plus should not be understood. It should be there. Figure 17, this graph reveals group and period trends for ionization energy. Analyzing data. Which element in period 2 has the lowest first ionization energy in period 3? Drawing conclusions. What is the group trend for first ionization energy for noble gases and alkali metals? C. Predicting. If you drew a graph for second ionization energy, which element would you have to omit and explain? Here is an example of a graph from hydrogen to cesium. You can see the flattened nature of the transition elements. You're going to have to explain the two little blimps that you see, beryllium and nitrogen, and magnesium and phosphorus, etc. Look at zinc. Why do you have that little peak with zinc? Same thing with cadmium. Why are the top peaks noble gases? Recall that the atomic size increases as the atomic number increases within a group. As the size of the atom increases, nuclear charge has a smaller effect on the electrons in the highest occupied energy level. So less energy is required to remove an electron from this energy level, and the first ionization energy is lower. Period trends in ionization energy. In general, the first ionization energy of representative elements tends to increase from left to right across a period. There are some exceptions that are based on electron filling of orbitals, and you should know those. This trend can be explained by the nuclear charge, which increases, and the shielding effect, which remains constant. The nuclear charge increases across the period, but the shielding effect remains constant. So there is an increase in the attraction of the nucleus for the electron. Thus, it takes more energy to remove an electron from an atom. Figure 18 on the next page summarizes the group and period trends for first ionization energy. So, you need to know the vertical trend and the horizontal trend. And the horizontal trend is not as easy as it sounds. There are some exceptions to the rule that they just gave. Figure 18, first ionization energy tends to increase from left to right across the period and decrease from top to bottom within a group. It's a little bit more complicated than that, but fair enough. Predicting which element would have the larger first ionization energy, an alkali metal in period 2 or an alkali metal in period 4. Remember, you have to play nuclear charge against shielding effect. So that's the trends in first ionization energy. The ionization energy, the first ionization energy tends to decrease as you go down a column or a family and increase as you go across, with two very notable exceptions for the S&P elements. For the transition elements, it's very flat, except when you get to zinc and cadmium. Okay, and you're going to have to do this lab that you're doing now, and you're working on it, relative to graphing the trends, or graphing the data and identifying the trends in ionic and atomic radii. So here is the next figure, 19. Atomic and ionic radii are an indication of the relative size of atoms and ions. The data listed in figure 19 is reported in picometers. This next graph, this next chart, this next table is very important to help you identify certain characteristics for bonding. When you're talking about, for instance, electronegativity, I'm not going to talk about this much. It's hard to see it really, but we will work on this in class. These are the S&Ps, and very, very important when it comes to helping you identify properties for electronegativity and for bonding. Helps a lot. Okay, trends in ionic size. During reactions between metals and nonmetals, metal atoms tend to lose electrons and nonmetal atoms tend to gain electrons. The transfer has a predictable effect on the size of the ions that form. Cations are always smaller than the atoms from which they form. Anions are always larger than the atoms from which they form. Figure 20 on the next page compares the relative sizes of the atoms and ions for three metals in group 1A. For each of these elements, the ion is much smaller than the atom. For example, the radius of sodium is 95 picometers, is about half the radius of the sodium atom of 191 picometers. Figure 20, this diagram compares the relative sizes of atoms and ions for selected alkali metals and halogens. The data are given in picometers, comparing and contrasting what happens to the radius when an atom forms a cation, when an atom forms an anion. So here is another figure, and you're looking at what happens to the corresponding cation for the metal and anion. So you're decreasing in atomic radii going from the metal to the cation and increasing going from the nonmetal to the anion. Look at those rather startling differences in ionic and atomic radii. When a sodium atom loses an electron, the attraction between the remaining electrons and the nucleus is increased. The electrons are drawn closer to the nucleus. Also, metals that are representative elements tend to lose all their outermost electrons during ionization. So the ion has one fewer occupied energy level. The trend is the opposite for nonmetals like the halogens in group 7A. For each of these elements, the ion is much larger than the atom. For example, the radius of a fluoride ion, 133 picometers, is more than twice the radius of a fluorine atom, 62 picometers. When, as the number of electrons increases, the attraction of the nucleus for any one electron decreases. Look back at figure 19. From left to right across a period, two trends are visible. A gradual decrease in the size of the positive ions, followed by a gradual decrease in the size of the negative ions. Figure 21 summarizes the group and periodic trends of ionic sizes. Well, you have in a particular period, the cations are first, and they're smaller than the corresponding anions, and there's a decrease in ionic size. And then the anions, which are larger as a group than the cations, there's also a decrease going from left to right of the ionic radii of the anions. Figure 21, the ionic radii for cations and anions decrease from left to right across the period and increase from top to bottom within groups. And here is the next slide, figure 21, will show you precisely how that occurs. We'll show you precisely how that occurs. Okay, here is the table, which contains trends in ionic size. So, vertical, you tend to, it generally increases as you go down a column or family, and the cations decrease, which are smaller than the corresponding anions in a period, and then the size of the anion also decreases, going from left to right. In chapter 7 and 8, you will study two types of bonds that can exist in compounds. Electrons are involved in both types of bonds. There is a property that can be used to predict the type of bond that will form during a reaction. This property is called electronegativity. Electronegativity is the ability of an atom of an element to attract electrons when the atom is in a compound. Scientists use factors such as ionization energy to calculate values for electronegativity. Table 2, next page, lists electronegativity values for representative elements in groups 1A through 7A. The plot is thickening. Okay. Here's the electronegativity. Notice fluorine is 4. That's in the upper right. Notice cesium is 0.7. That's the lower left. And the electronegativity trend tends to decrease diagonally going from fluorine to cesium, taking into account nuclear charge and shielding effect, etc. Those two things have to be considered when looking at electronegativity. The elements are arranged in the same order as in a periodic table. The noble gases are omitted because they do not form many compounds. The data in Table 2 is expressed in units called Paulings. Linus Pauling won a Nobel Prize in Chemistry for his work on chemical bonds. He was the first to define electronegativity. In general, electronegativity values decrease from top to bottom within a group. For representative elements, the values tend to increase from left to right across a period. Metals at the far left of the periodic table have low values. It's important to understand why those are low and why fluorine, oxygen, and chlorine are high. Very important to know that information. By contrast, nonmetals at the far right, excluding noble gases, have high values. The electronegativity values among the transition metals are not as regular. The least electronegative element is cesium, with an electronegativity of 0.7. It has the least tendency to attract electrons or bonded electrons. When it reacts, it tends to lose electrons and form positive ions. The most electronegative element is fluorine, with a value of 4. Because fluorine has such a strong tendency to attract electrons, when it is bonded to any other element, it either attracts the shared electrons or forms a negative ion through ionic bonding. Figure 22 on the next page shows the trends for atomic size, ionization energy, ionic size, and electronegativity in groups 1A through 8A. These properties vary within groups and across periods. The trends that exist among these properties can be explained by variations in atomic structure. The increase in nuclear charge within groups and across periods explains many trends within groups. An increase in shielding has a significant effect. So, the last slide we're going to see kind of summarizes. You should kind of take this next figure 22, and imprint it on your brain. Figure 22, properties that vary within groups and across periods include atomic size, ionic radius, ionization energy, electronegativity, nuclear charge, and shielding effect. Interpreting diagrams, which properties tend to decrease across a period, which properties tend to decrease across a period. So let's look at these. So we have the various things. We have atomic size is increasing. Ionic size is increasing as you go down. Ionization energy decreases, electronegativity decreases, nuclear charge increases, and shielding increases. And then across the columns, you have atomic size decreases, ionization increases, electronegativity increases, shielding charge increases, and shielding is constant. No, nuclear charge increases and shielding is constant. Okay, that's it. That's it for now. See you in chapter 7 and 8 on bonding. Have a great day and goodbye.